हेलो एवरीवन, वंस अगेन वेलकम बैक टू आवर चैनल बीट द नीट। आई होप कि आप सब लोगों की तैयारी बहुत अच्छी चल रही होगी। एंड आज मैं बनाने वाली हूँ ऑडियो बुक क्लास 11th यूनिट 7 इक्विलिब्रियम चैप्टर की। ये चैप्टर थोड़ा सा लेंदी है, इसलिए इसके मैं 2 पार्ट में रिकॉर्ड करूंगी। सो आज मैं इसका फर्स्ट पार्ट रिकॉर्ड कर रही हूँ एंड सेम डे ही आपको इसका सेकेंड पार्ट प्रोवाइड कर दूंगी। बच्चों, अगर ये ऑडियो बुक्स आपकी रिवीजन में हेल्प कर रही हैं तो इसको प्लीज अपने दोस्तों के साथ भी शेयर करिए और इसको लाइक भी जरूर करिएगा। और अगर आप मेरे चैनल पे नए हैं तो इसको सब्सक्राइब भी कीजिएगा। चलिए टाइम वेस्ट नहीं करते हैं और जल्दी से स्टार्ट करते हैं। Chemical equilibria are important in numerous biological and environmental processes. For example, equilibria involving O2 molecules and the protein hemoglobin play a crucial role in the transport and delivery of O2 from our lungs to our muscles. Similar equilibria involving CO molecules and hemoglobin account for the toxicity of CO. When a liquid evaporates in a closed container, molecules with relatively higher kinetic energy escape the liquid surface into the vapor phase, and number of liquid molecules from the vapor phase strike the liquid surface and are retained in the liquid phase. It gives rise to a constant vapor pressure because of an equilibrium in which the number of molecules leaving the liquid equals the number returning to liquid from the vapor. We say that the system has reached equilibrium state at this stage. However, this is not a static equilibrium and there is a lot of activity at the boundary between the liquid and the vapor. Thus, at equilibrium, the rate of evaporation is equal to the rate of condensation. It may be represented by H2O, reversible reaction, that is liquid, and it is forming vapor. The double half arrows indicate that the process in both directions are going on simultaneously. The mixture of reactants and products in the equilibrium state is called an equilibrium mixture. Equilibrium can be established for both physical processes and chemical reactions. The reaction may be fast or slow depending on the experimental conditions and the nature of reactants. When the reactants in a closed vessels are a particular temperature react to give products, the concentration of the reactants keep on decreasing while those of products keep on increasing for some time alter which there is no change in the concentration of either of the reactants or products. This stage of the system is the dynamic equilibrium and the rates of the forward and reverse reactions become equal. It is due to this dynamic equilibrium stage that there is no change in the concentrations of various species in the reaction mixture. Based on the extent to which the reactions proceed to reach the state of chemical equilibrium, these may be classified in these groups. Number 1. The reactions that proceed nearly to completion and only negligible concentration of the reactants are left. In some cases, it may not be even possible to detect these experimentally. Number 2. The reactions in which only small amounts of products are formed and most of the reactants remain unchanged at equilibrium stage. Number 3. The reactions in which the concentration of the reactants and products are comparable when the system is in equilibrium. The extent of a reaction in equilibrium varies with the experimental conditions such as concentration of reactants, temperature, etc. Optimization of the operational conditions is very important in industry and laboratory so that the equilibrium is favorable in the direction of desired product. Some important aspects of equilibrium involving physical and chemical processes are dealt in this unit along with equilibrium involving ions in aqueous solution, which is called as ionic equilibrium. 7.1 Equilibrium in physical processes. The characteristics of system at equilibrium are better understood if we examine some physical processes. The most familiar examples are phase transformation processes, example solid to liquid, liquid to gas, solid to gas, and the vice versa. 7.1.1 Solid liquid equilibrium. Ice and water kept in a perfectly insulated thermos flask. There is no exchange of heat between its content and the surroundings. At 273 Kelvin and the atmospheric pressure are in equilibrium state and the system shows interesting characteristic features. We observe that the mass of ice and water do not change with time and the temperature remains constant. However, the equilibrium is not static. The intense activity can be noticed at the boundary between ice and water. Molecules from the liquid water collide against ice and adhere to it, and some molecules of ice escape into liquid phase. There is no change of mass of ice and water as the rates of transfer of molecules from ice into water and the reverse transfer from water into ice are equal at atmospheric pressure and 273 Kelvin. It is obvious that ice and water are in equilibrium only at particular temperature and pressure. For any pure substance at atmospheric pressure, the temperature at which the solid and liquid phases are at equilibrium is called the normal melting point or normal freezing point of the substance. The system here is in dynamic equilibrium, and we can infer the following. Number 1. Both the opposing processes occur simultaneously. Number 2. Both the processes occurs at the same rate so that the amount of ice and water remains constant. 7.1.2 Liquid vapor equilibrium. This equilibrium can be better understood if we consider the example of a transparent box carrying a U-tube with mercury manometer. Drying agent like anhydrous calcium chloride or phosphorus pentaoxide is placed for a few hours in the box. After removing the drying agent by tilting the box on one side, a watch glass or petri dish containing water is quickly placed inside the box. It will be observed that the mercury level in the right limb of the manometer slowly increases and finally attains a constant value. That is, the pressure inside the box increases and reaches a constant value. Also, the volume of water in the watch glass decreases. Figure 7.1. Initially, there was no water vapor or very less inside the box. 7.1 Measuring equilibrium of vapor pressure of water at a constant temperature. As water evaporated, the pressure in the box increased due to addition of water molecules into the gaseous phase inside the box. The rate of evaporation is constant. However, the rate of increase in pressure decreases with time due to condensation of vapor into water. Finally, it leads to an equilibrium condition when there is no net evaporation. This implies that the number of water molecules from the gaseous state into the liquid state also increases till the equilibrium is attained. That is, rate of evaporation is equal to the rate of condensation. At equilibrium, the pressure exerted by the water molecules at a given temperature remains constant and is called the equilibrium vapor pressure of water, or just vapor pressure of water. Vapor pressure of water increases with temperature. If the above experiment is repeated with methyl alcohol, acetone and ether, it is observed that different liquids have different equilibrium vapor pressure at the same temperature, and the liquid which has a higher vapor pressure is more volatile and has lower boiling point. If we expose 3 watch glasses containing separately 1 ml each of acetone, ethyl alcohol and water to atmosphere and repeat the experiment with different volumes of the liquids in a warmer room, it is observed that in all such cases the liquid eventually disappears and the time taken for complete evaporation depends on number 1, the nature of the liquid, number 2, the amount of the liquid, and number 3, the temperature. When the watch glass is opened to the atmosphere, this rate of evaporation remains constant, but the molecules are dispersed into large volume of the room. As a consequence, the rate of condensation from vapor to liquid state is much less than the rate of evaporation. These are open systems and it is not possible to reach equilibrium in an open system. Water and water vapor are in equilibrium position at atmospheric pressure, that is 1.013 bar, and at 100 degrees Celsius in a closed vessel. The boiling point of water is 100 degrees Celsius at 1.013 bar pressure. For any pure liquid at 1 atmospheric pressure, that is 1.013 bar, the temperature at which the liquid and vapors are at equilibrium is called the normal boiling point of the liquid. Boiling point of the liquid depends on the atmospheric pressure. It depends on the altitude of the place. At high altitude, the boiling point decreases. 7.1.3 Solid vapor equilibrium. Let us now consider the systems where solids sublime to vapor phase. If we place solid iodine in a closed vessel, after some time the vessel gets filled up with the violet vapor and the intensity of the color increases with time. After a certain time, the intensity of color becomes constant and at this stage equilibrium is attained. Hence, solid iodine sublimes to give iodine vapor and the iodine vapor condenses to give solid iodine. The equilibrium can be represented as I2 solid and here is the I2 vapor. Other examples showing this kind of equilibrium, that is a camphor solid to the camphor vapor and an H4Cl solid to the H4Cl vapor. 7.1.4 Equilibrium involving dissolution of solid or gases in liquids. Solids in liquids. We know from our experience that we can dissolve only a limited amount of salt or sugar in a given amount of water at room temperature. If we make a thick sugar syrup solution by dissolving sugar at higher temperature, sugar crystals separate out if we cool the syrup to the room temperature. We call it at a saturated solution when no more of solute can be dissolved in it at a given temperature. The concentration of the solute in a saturated solution depends upon the temperature. In a saturated solution, a dynamic equilibrium exists between the solute molecules in the solid state and in the solution. Sugar solution converted into the sugar solid, and the rate of dissolution of sugar is equals to the rate of crystallization of sugar. Equality of the two rates and dynamic nature of equilibrium has been confirmed with the help of radioactive sugar. If we drop some radioactive sugar into saturated solution of non-radioactive sugar, then after some time radioactivity is observed both in the solution and in the solid sugar. Initially, there were no radioactive sugar molecules in the solution, but due to dynamic nature of equilibrium, there is exchange between the radioactive and non-radioactive sugar molecules between the two phases. The ratio of the radioactive to non-radioactive molecules in the solution increases till it attains a constant value. Gases and liquids. When a soda water bottle is opened, some of the carbon dioxide gas dissolved in it fizzes out rapidly. The phenomena arises due to difference in solubility of carbon dioxide at different pressures. There is equilibrium between the molecules in the gaseous state and the molecules dissolved in the liquid under pressure, that is, CO2 gas converted into the CO2 in solution. This equilibrium is governed by Henry's law, which states that the mass of a gas dissolved in a given mass of a solvent at any temperature is proportional to pressure of the gas above the solvent. This amount decreases with increase of temperature. The soda water bottle is sealed under pressure of gas when its solubility in water is high. As soon as the bottle is opened, some of the dissolved carbon dioxide gas escapes to reach a new equilibrium condition required for the lower pressure, namely its partial pressure in the atmosphere. This is how the soda water in bottle, when left open to the air for some time, turns flat. It can be generalized that: number 1, for solid to liquid equilibrium, there is only one temperature melting point at 1 atmospheric at which the two phases can coexist. If there is no exchange of heat with the surroundings, the mass of the two phases remain constant. Number 2, for liquid vapor equilibrium, the vapor pressure is constant at a given temperature. Number 3, for dissolution of solids and liquids, the solubility is constant at given temperature. Number 4, for dissolution of gases in liquids, the concentration of gas in liquid is proportional to the pressure, that is concentration of the gas over the liquid. These observations are summarized in table 7.1. Here you can see some features of physical equilibria. That is the process and the conclusion. In liquid to vapor, that is H2O liquid to the H2O vapor, that is PH2O constant at given temperature. In the solid to liquid phase, the melting point is fixed at constant pressure. And in the solute to solute solution, just like sugar to the sugar solution, the concentration of solute in solution is constant at a given temperature. Gas to gas aqueous form, that is CO2 gaseous to CO2 aqueous form, that is constant at a given temperature. 7.1.5 General characteristics of equilibria involving physical processes. For the physical processes discussed above, following characteristics are common to the system at equilibrium. Number 1, equilibrium is possible only in a closed system at a given temperature. Number 2, both the opposing processes occur at the same rate and there is a dynamic but stable condition. Number 3, all measurable properties of the system remain constant. Number 4, when equilibrium is attained for a physical processes, it is characterized by constant value of one of its parameters at a given temperature. Table 7.1 lists such quantities. Number 5, the magnitude of such quantities at any stage indicates the extent to which the physical processes has proceeded before reaching equilibrium. 7.2 Equilibrium in chemical processes, that is dynamic equilibrium. Analogous to the physical system, chemical reaction also attain a state of equilibrium. These reactions can occur both in forward and backward directions. When the rates of the forward and reverse reactions become equal, the concentration of the reactants and the products remain constant. This is the stage of chemical equilibrium. This equilibrium is dynamic in nature as it consists of forward reaction in which the reactants give products and reverse reaction in which product gives the original reactants. For a better comprehension, let us consider a general case of reversible reaction, that is A plus B reversible C plus D. With passage of time, there is accumulation of the product C and D and depletion of the reactants A and B, figure 7.2. This leads to a decrease in the rate of forward reaction and an increase in the rate of reverse reaction. Here you can see figure 7.2, that is the attainment of chemical equilibrium. Eventually, the reaction occurs at same rate and the system reaches a state of equilibrium. Similarly, the reaction can reach the state of equilibrium even if we start with only C and D. That is, no A and B being present initially, as the equilibrium can be reached from either direction. The dynamic nature of chemical equilibrium can be demonstrated in the synthesis of ammonia by Haber's process. In a series of experiments, Haber started with known amounts of dinitrogen and dihydrogen maintained at high temperature and pressure, and regular intervals determined the amount of ammonia present. He was successful in determining also the concentration of unreacted dihydrogen and dinitrogen. Figure 7.4, page number 191, shows that after a certain time, the composition of the mixture remains the same even though some of the reactants are still present. This constancy in composition indicates that the reaction has reached equilibrium. In order to understand the dynamic nature of the reaction, synthesis of ammonia is carried out with exactly the same starting condition of partial pressure and temperature, but using D2, that is deuterium, in place of H2. The reaction mixture starting either with H2 or D2 reach equilibrium with the same composition, except that D2 and ND3 are present instead of H2 and NH3. After equilibrium is attained, these two mixtures are mixed together and left for a while. Later, when this mixture is analyzed, it is found that the concentration of ammonia is just the same as before. However, when this mixture is analyzed by a mass spectrometer, it is found that ammonia and all deuterium containing forms of ammonia, NH3, NH2D, NHD2 and ND3, and dihydrogen and its deuterated forms H2, Hd and D2 are present. Thus, one can conclude that scrambling of H and D atoms in the molecule must result from a continuation of the forward and reverse reactions in the mixture. If the reaction had simply stopped when they reached equilibrium, then there would have been no mixing of isotopes in this way. Use of isotope deuterium in the formation of ammonia clearly indicates that chemical reaction reach a state of dynamic equilibrium in which the rates of forward and reverse reaction are equal and there is no net change in composition. Equilibrium can be attained from both sides, whether we start reaction by taking H2 and N2 and get NH3, or by taking NH3 and decomposing it into the N2 and H2. N2 plus 3H2 gives out 2NH3. 2NH3 gives out N2 plus 3H2. Similarly, let us consider the reaction H2 plus I2 gives out 2HI, and if we start with equal initial concentration of H2 and I2, the reaction proceeds in the forward direction and the concentration of H2 and I2 decreases while that of HI increases until all of these become a constant at equilibrium, figure 7.5. We can also start with HI alone and make the reaction to proceed in the reverse direction. The concentration of HI will increase and concentration of H2 and I2 will increase until they all become constant when equilibrium is reached, figure 7.5. If total number of H and I atoms are same in a given volume, the same equilibrium mixture is obtained whether we start it from pure reactants or pure products. You can see figure 7.4 here, that is a depiction of equilibrium for the reaction. And this is the figure 7.5, that is chemical equilibrium in the reaction H2 plus I2 gives out 2HI can be attained from either direction. We have one separate paragraph, that is the dynamic equilibrium, and that is a student activity. You can see here. That is a figure 7.3. Now come to the 7.3 law of equilibrium and equilibrium constant. A mixture of reactants and products in the equilibrium state is called an equilibrium mixture. In this section, we shall address a number of important questions about the composition of equilibrium mixtures. What is the relationship between the concentration of reactants and products in an equilibrium mixture? How can we determine equilibrium concentration from initial concentrations? What factors can be exploited to alter the composition of an equilibrium mixture? The last question in particular is important when choosing condition for synthesis of industrial chemicals such as H2, NH3, CaO, etc. To answer these questions, let us consider a general reversible reaction, A plus B reversible C plus D, where A and B are the reactants, C and D are the products in the balanced chemical equation. On the basis of experimental studies of many reversible reactions, the Norwegian chemist Cato, Maximilian Guldberg and Peter Wag proposed in 1864 that the concentration in an equilibrium mixture are related by the following equilibrium equation. Kc is equals to CD upon AB, where Kc is the equilibrium constant and the expression on the right side is called the equilibrium constant expression. The equilibrium equation is also known as the law of mass action because in the early days of chemistry, concentration was called active mass in order to appreciate their work better. Let us consider reaction between gases S2 and I2 and carried out in a sealed vessel at 731 Kelvin. H2 plus I2 and gives out 2Hi and 1 mole of H2, 1 mole of I2 and it is forming the 2 mole of Hi. 6 sets of experiment with varying initial condition were performed, starting with only gases S2 and I2 in a sealed reaction vessel in first 4 experiment and only Hi in other 2 experiment. Experiment 1, 2, 3 and 4 were performed taking different concentration of S2 and or I2, and with time it was observed that intensity of the purple color remained constant and equilibrium was attained. Similarly, for experiment 5 and 6, the equilibrium was attained from the opposite direction. Data obtained from all 6 sets of experiments are given in table 7.2. It is evident from the experiments 1, 2, 3 and 4 that number of moles of dihydrogen reacted is equal to the number of moles of iodine reacted is equals to the half number of moles of Hi formed. Also, experiment 5 and 6 indicates that H2 is equals to I2. Knowing the above facts, in order to establish a relationship between the concentration of reactants and products, several combinations can be tried. Let us consider the simple expression, that is Hi upon H2 and I2. It can be seen from table 7.3 that if we put the equilibrium concentration of the reactant and products, the above expression, here you can see the table 7.2, initial and equilibrium constant of H2 and Hi, different values it is. And here is the table 7.3, that is the expression involving the equilibrium concentration of reactant, that is H2 plus I2 gives out 2Hi. So here the different experiment, all the 6 experiments and all the different values you can get. Rest part of the chapter you will get in the part 2. So just revise up to here and then I will provide you the next part of it. So take care everyone. Just stay tuned with me. Bye-bye.